All right, so we're going to look at flexural shear and punching shear now. So what we'll cover in this the course of this talk is first of all just some general requirements for shear. Then we'll, on the flexural side of things, we'll look at members not requiring design shear reinforcement. And then we'll look at the rules for how things differ when you have shear reinforcement. And things are actually reasonably different in Eurocodes compared to previous British practice. And then we'll finish up by having a quick look at punching shear. And the example that follows is actually more to do with punching than it is to do with flexural shear. But once again, in the book or on the Bridges site, there are plenty of examples for flexural shear as well. So there are various terms again that are used that you'll see in the shear section. They're reasonably straightforward, but it's worth just going through what they all mean. VED, hopefully we're getting the feel by now that is an action rather than a resistance. ED, effect design, so VED is the shear force within the member. And then there are various resistances which the code flags up. So we have VRD, C. That's basically the shear resistance of a section without shear reinforcement in it. So the C is just standing for concrete, basically the concrete resistance on its own. We have VRDS, where S is basically referring to the shear reinforcement. So VRDS is the resistance based on shear reinforcement. And then we have VRD max, which is the equivalent of V max in BS500, and this is just simply the maximum stress or maximum shear force, if you like, that you can actually apply to the concrete section, irrespective of what reinforcement you put in it, such that the concrete doesn't crush. In the same way as BS500 shear design was carried out, you'd normally done the flexural design first and had all the cross-section and dimensions sorted out before you went and you did the shear design. When you do the shear design, you're effectively just checking against shear and providing shear reinforcement. The same is really assumed in the Eurocode. So you'll find that the shear resistances require you to know the flexural lever arm, Z, because that's a measure of the depth that you've got available for shear, and it will also assume for sections without links, you will also assume that you already know what the flexural reinforcement is. You'll need that for calculating the shear reinforcement, but for calculating shear resistance on the concrete. So there's no principal difference in the way we go about shear design. It's exactly the same. But there are a few extra slight differences. So, for example, when we're carrying out our shear design, it's allowable to include inclined components of both the concrete stress field and also reinforcement. So if we have a horizontal section, then there aren't any inclined components of either the flange or the reinforcement. But if we have a strange little fish-bellied shape like that, this is an end support, and we've got the tension reinforcement here and the compression field here, then the compression force and the reinforcement force are both actually carrying some of the shear. And so we can, depending on how you look at it, we can either deduct those components from the applied shear, or we can add them to the shear resistance. And that's just pure statics. We've got shear force on the end there, and they've obviously been carried by those components in part. Just switch that mute on because I think we're going to get horrible echo otherwise. So that's one difference. The other difference, which we'll come to in a minute, is that if we don't if we don't actually exceed the shear resistance of the concrete, then we don't need to put links in other than minimum links for a beam. But for a slab, we don't need to put links in at all. As soon as we exceed BRDC, the concrete strength, then when we start adding links in, we can't any longer add the two components together. As soon as the concrete capacity is exceeded, then we have to design entirely on links. But that isn't as desperate as it sounds, because we're allowed to vary the truss angle in the design for shear, which we'll talk about in a minute, which actually means you get much higher resistances generally out of the Eurocodes than you did out of BS500. So just sort of starting off with reinforced concrete without any links. It's a pretty simple expression, and it's very similar in the Eurocode to the one that was in BS500. So we have VRDC here, the shear force resistance of the concrete on its own, which is a function of rho 1, which is the reinforcement ratio, the longitudinal reinforcement ratio in the tension zone. It's got the concrete cylinder strength in there as well, FCK, as you might expect. There is a depth factor, K, which is not the same as the depth factor in BS500, but it's doing the same job. And then there's a parameter CRDC, which is a nationally determined parameter, but it has a recommended value in the Eurocodes, and the UK National Annex just accepts that. So it says that CRDC is 0.18 divided by the material factor gamma C, and gamma C is 1.5. I'll just mention now, in case I forget coming back later, I say the Eurocode, the National Annex accepts CRDC as 0.18 over gamma C. What it actually does is makes a slight tweak to that, and it redefines it as 0.18 over gamma C times 2D over AV to introduce some shear enhancement. That's not because the Eurocode doesn't have shear enhancement. It's because the Eurocode, the way it's written at the moment, tries to do it in a different way, which we in the UK consider is incorrect. So it's a bit of a fudge, and I'll come on to that in a minute. What you'll find is that the resistance just for shear, just for the concrete alone, if you compare with the resistance from BS500, is quite similar. However, if you take the gamma factors off, then the characteristic resistances are not that similar. The Eurocode is a bit higher. And the reason for that is quite simple. The gamma factor of 1.5 here appears in the equation in the Eurocodes outside all of these terms to the root of a third, whereas in the BS500 the gamma factor of 1.5 is effectively within the equation of the concrete strength, and therefore the gamma factor is effectively smaller in BS500. So although the design resistances come out the same, the characteristic resistances are not the same, and that actually led to a bit of argument during drafting, because the purists were basically saying the characteristic values, i.e. before you've applied the material factors, really ought to match between codes and the test evidence, and they actually don't. They only match when you've applied the gamma factors. There's also, irrespective of what longitudinal reinforcement you put in, there's a minimum resistance that the concrete provides. So that's just a function of the V min of the concrete grade, and again those minimum concrete resistances are again very similar to what we had from BS500. Just jumping back to the previous one, the term I didn't mention is sigma CP, which is the effects of axial force. So if you have axial compression, then that increases your shear resistance. And there was a similar term in BS500 for columns, but this has a much more significant effect. The effect in BS500 was very small. This is actually reasonably significant. The other thing to notice is that sigma CP acts in both directions. So if it's compressive, it improves the situation, and if it's tensile, it actually makes it worse. So if you have, for example, a deck slab that's in overall global tension, because it's participating in the global direction, and then you put local wheel loads on top of that and check for shear, then there is actually, or can be, a reduction because of the global tension that's there, which wasn't present in BS500. I'd say the shear is a bit different in the Eurocode. I mean, the Eurocode itself does it the way that's shown on this diagram. So in the past, in BS500, and the way we've now fudged the UK National Annex by putting 2D over AV into CRDC, we've basically calculated the shear force. We then looked at the section that we're checking, and we've enhanced the resistance by a factor 2D over AV. So that's what the UK National Annex is now telling you to do. What the Eurocode actually tells you to do is to unenhance the load. And it looks the same, which is why we didn't spot it when the Germans snuck it in at the 11th hour in the last part of drafting of the code. What it says is you look at each load. So in the lower figure here, the load that's at a distance AV, AV1 from the support, we would reduce its contribution by multiplying it by AV over 2D. And then the other load that's further away, we would reduce its contribution by, in this case, 2AB over 2D. That's not the same. If you've got 1 point load, then the two methods are the same. But if you've got more than 1 point load, then they've obviously got different AVs. And so the old British method is a lot more economic than the proposed Eurocode method. And there are some real practical problems with trying to unenhance the load by multiplying by this factor AV over 2D for each load. They're almost too numerous to list, really. If you've got a UDL, then it becomes an integration for every sort of small piece of UDL that's from the support. If you use an autoloader, then you actually don't really know where your loads came from, so it's pretty impossible to unpick them. But it's still easy to check a section by reducing it or by increasing its resistance. And the other real danger is if you start reducing loads to calculate your shear, if you actually do that in the computer model, then there's a real danger that when you come to design your substructure and your columns, you've actually got artificially reduced loads, so that they've just been reduced solely for a fudge for shear. So there are lots and lots of dangers. It also doesn't match test results. And there was some very extensive tests done in Stuttgart in the 1960s, which shows very good agreement with the old BS500 approach and absolutely abysmal agreement with the current Eurocode approach. So it will change, probably in 5 years' time, with the next update. So for now, using the UK National Annex, we enhance the resistance in the same way as before. But clearly, if you do that, don't unenhance the load as well. We can't do it twice. So that's without any links. If we have links, then we have the same sort of truss model that was hidden behind BS500. But whereas BS500 had a truss model where we had inclined compression struts which were fixed at 45 degrees. It didn't tell you that in the code, but that was the background. We had struts fixed at 45 degrees. In the Eurocode, we can vary the angle of those struts from 45 degrees to a much flatter angle, down to 21.8 degrees. And as you'll see from the formula in a minute, the significance of flattening the truss angle off is that the concrete struts basically cross more links. And if they cross more links, they involve more links in the shear resistance calculation, and we can get a lot more force out of the links. But, as I say, you can't add the concrete term to the link term. So if you want to design with a 45-degree truss, you will get a lower resistance than you used to get with BS500. The real key thing to get across with this is this choice of truss angle is entirely the designer's. You can choose whatever you like between 45 degrees and 21.8 degrees, but then you have to live with the various consequences of having done that, because it follows through in lots of different formulae after that. So basically we have two resistance formulae that we have to satisfy. One is based on the link resistance, and the other is based on the crushing of the concrete, VRD max, which, as I say, is the equivalent to the old V max in BS500. The other thing you'll notice, as somebody pointed out here before we started, is that the Eurocode allows you to incline your shear links as well. And you can get some further economy out of inclining shear links, and the optimum angle is having them inclined over at 45 degrees. But don't do this for bridge works, because it's thoroughly impractical to construct, because you end up with links poking through construction joints, which isn't really very practical. And unless you can fabricate everything in one piece and concrete it in one piece, it's a nightmare for construction joints. So vertical links, I think, please still. The formula for based on links is this one here. So you can see we've got a term at the start that looks exactly the same as the one in BS500. So the shear resistance is AS over S, which is the link area per metre, times Z. We use Z as the depth rather than D in the Eurocode, Z being the lever arm, which for reinforced concrete you can take as 0.9D without any calculation, even if it isn't 0.9D. But for prestressed concrete, you must calculate specifically what Z actually is from the ultimate limit state stress block, and you cannot assume it's 0.9D. So the first part, if we ignore the cot thetas and cot alphas, is just the same as the link contribution from BS500. But we do have these other terms, cot theta plus cot alpha. Alpha is the angle of the stirrups. So as I say, if you keep them vertical like we should do, then the alpha just becomes 90 degrees, and the effect of cot alpha sort of disappears from the equation. Then we're left with cot theta, and theta is the assumed compression truss angle and say this is the thing that you can vary to suit your requirements. Basically what happens is, as I mentioned earlier, if you go for a 45-degree truss angle, which is the steepest, then cot theta becomes 1, and all of that lot will disappear, and you'll be left with basically the same formula as in BS 500, but without the concrete term. If I choose theta to be the flattest angle that I'm allowed, of 21.8 degrees, then cot theta becomes 2.5, and we essentially end up with 2.5 times what we used to get out of BS 500. But again, we can't add the concrete term in. So the choice is yours. You can have anything between 1 times that or 2.5 times that, but it will then have a knock-on effect for both the longitudinal reinforcement, as you'll see in a minute, and also for the crushing resistance. Because as fast as the link provision goes down with flatter truss angles, what you find when you look at this second equation for VRD max, a flatter truss angle will actually reduce the maximum shear stress that you could actually put on the section. So as one goes up, the other goes down. So if you've got a very thick section, like most bridge beams normally are, and your stresses are nowhere near V max, then you want to go for a flat truss angle basically and minimise the number of links that you've got. But if weight is really, really important to you, so maybe talking about the other extent of structure, a balanced cantilever or something, where you want to keep the webs actually very thin to keep the overall weight down, then it may be that you want to make the webs as thin as possible, in which case you want VRD max to be as big as possible. And in that case you would then go for a steep truss angle to maximise VRD max, but you end up providing more links. That's a balancing act. So for other sections, you can maybe come up with an optimum whereby you get both failing at the same time. But in general, VRD max is not critical, and then you're best off going for a flat truss angle and minimising the number of links. You'll also find if you put numbers into VRD max, they typically come out higher than the equivalent Vmax was anyway in BS 500. So I might not get the number precisely right, but for a grade 50 concrete, if you were designing pre-stress to BS 500, for a 50 concrete, I think the limiting shear stress was 5.3 megapascals. In the Eurocode, if it's a pre-stressed member, it depends on the amount of pre-stress you've got, but that 5.3 might well be 8. So you're starting off with quite a larger number. Just to demonstrate that, we just go back to a really simple rectangular structure, rectangular beam. Same one we looked at the bending for. So we've got some shear links here, 16 diameter bars at 200mm centres. If we were basically to design or assess that situation to BS 500, then we would effectively be using this 45-degree fixed truss angle, and we would get a shear resistance of 1100 kilonewtons. The figure in brackets is basically what happens if we ignore the 0.4 term in BS 500. This is the term where we have to deduct a certain amount of stress to allow for sort of fatigue in the links. So we get 1259 if we ignored that term. And the crushing resistance based on V max, it's a great big wide section that, so you wouldn't be expecting to get anywhere near it. And the crushing resistance therefore comes out a lot bigger. So the governing resistance is based on the links they're provided. If we do the same calculation to Eurocode 2 and we use a 45-degree truss angle, then we're basically using the same assumptions as BS 500 in terms of links, but we're not allowing to add a concrete term. So we're pretty much the same. We get much the same answer. We get 1238 kilonewtons out of the links. But the crushing resistance is a fair bit higher, as I say, just because crushing resistances tend to come out a bit higher in BS 500, in Eurocode 2 if you stick with the 45-degree angle. If we now use the flattest truss angle, in this case, the 21.8 degrees, then we get 2.5 times more capacity out of the links than we would have done with a 45-degree angle. But the crushing resistance actually drops down by having a flatter truss angle. So the shear resistance is still governing on links, but we have reduced the crushing resistance. So you can imagine for different sections it's possible by going from the steep angle to the flat angle that these two could actually cross over, and you might end up making the crushing critical, but not if you've got a lot of concrete like we have in this situation here. So I say generally it's going to be advantageous to go for the flat truss angle to minimise the amount of links that you've got. The further caveat on that is that not only does the truss angle affect the maximum stress, the shear, the V max, but it also has an implication for the design of your longitudinal reinforcement. If you think back to BS500, there was when you were doing a shear design, there was a term for the additional longitudinal reinforcement that you needed to provide for the shear, and there is a similar term in the Eurocodes for that, and it's basically the term here. The additional reinforcement we need to provide is 0.5 times the shear force times cot theta minus cot alpha. If we make that 45 degrees, we get the same additional longitudinal reinforcement requirement that we had in BS500. If we go to a flatter truss angle, we get more longitudinal reinforcement required than in BS500. So there's a potential penalty in the longitudinal reinforcement by saving in links. But the last thing to come back to here is that the intention in the Eurocode and in BS500 is the same, in that at the points of maximum bending moment, it is never the intention to provide more reinforcement than you need for bending. So this additional force for shear was never supposed to add at the points of maximum bending in hog or sag. All it actually does is do what we've got in this diagram here. It basically extends out the bending moment envelope. So at the peak moment positions it has no effect, but coming away from the peak bending position, it means we have to continue that peak provision some distance out. And I think the Eurocode is much better in demonstrating what you're supposed to do. So it does talk about this additional force, but it also does it in a different way, or a different way of explaining it. And says another way of looking at this is start with your bending moment diagram, and if you want to make the allowance for the extra requirement for shear in the longitudinal reinforcement, just basically extend out your bending moment diagram by this amount here, AL each side. And again, this is to do with the effective depth, sort of the lever arm and the truss angle that you've chosen. And I think what this makes clear is that the extra longitudinal reinforcement is actually nothing about really adding more reinforcement. It's about extending the curtailments further out. And it's kind of very simple terms. If you think about it, the truss model is just that. It's a strut coming down, picking up a piece of reinforcement, and then then a tie coming up and another strut coming down at an angle. If you make the truss angle flatter, you have to go further before it picks up the piece of reinforcement that you're considering. So it's all about extending the provision of reinforcement, not about adding at the points of maximum bending moment. So if you've got a short span and you don't curtail your reinforcement at all, it's to say you've got T20s in the soffit and it's just 20s all the way through, this doesn't mean anything at all, because you're not curtailing the reinforcement. If you've got a longer span and you're stepping your longitudinal reinforcement down from sort of 40 to 32 to 25, it will push your curtailment points out. So in that situation, you will actually be physically providing more longitudinal steel in the span to suit putting fewer links in. That makes sense. So there's a lot of power to the designer to decide where you want to put the steel, and you need to kind of understand those things to be able to do it, to design efficiently. It's also quite a powerful assessment tool as well, even though I come back to where I started, which is you're not really supposed to use it for assessment, but there's no real reason why you can't use that particular clause for assessment. If you've got beams with links, as we're talking about, then there are some provisions on shear reinforcement, shear enhancement again. You generally shouldn't need, for beams with links, you generally shouldn't need to use shear enhancement, because the variable angle truss model and the fact that you get more out of the links normally means you've got plenty of provision. But if you want to specifically look at short shear span behaviour, then you have to kind of slightly change your approach. Where you've got links, I'm afraid you do have to work with the definition that the Eurocode provides and reduce the actual applied forces by the factor beta, so by a factor AV over 2D for proximity of the supports. And then you compare that reduced shear force against basically the shear force, the vertical shear force that you've got in the span region, which is, if you've got a distance AV between the two loads, you have to look at a portion of 0.75 AV to the middle 3/4, if you like, and look at what link provision you've got in that area, and then you basically just carry that reduced shear on those links in that short length. And the reason you have to consider a length of 0.75 instead of the full length of AV is simply because test results show that the links nearest the support and nearest the load just actually don't participate in the mechanism. They don't get strained at all. It's only the ones in the middle 3/4 that actually get loaded. As I say, generally it should be simple enough just to ignore this short shear span behaviour and just use the variable angle truss model irrespective of where the loads are. There isn't actually very much to say about pre-stressed concrete because in the same way as for bending it's the same rules. For pre-stressed concrete it's the same rules as well. We don't have separate sections. So if you have no links in your pre-stressed concrete, so it's probably a pre-stressed concrete slab rather than a beam, then we have to work from exactly the same expression that we use for reinforced concrete, and the only benefit you get from pre-stressing is in the sigma CP term. This is the actual axial stress that's been applied by the pre-stressing force. But otherwise, everything is exactly the same. When you come to calculate the ASL, the area of steel, then you can include bonded pre-stressing in that, only if it's bonded. If it's unbonded, you can't consider it. And if you've got combinations of pre-stressed steel and untensioned steel, then when you calculate the effective depth, then again you can use a weighted mean value based on the centre of the steel area irrespective of the strength, which is the same definition that we had in the BS500. So we don't need to weight on the basis of the strength. If we've got ducts in the section, then they have to be taken into account. The rules are if you've got a grouted metal duct, and it has to be metal, then as long as the duct diameter is less than the web width divided by 8, then you can just ignore it altogether. It doesn't have any effect on the shear resistance. If they're bigger than the width over 8, then if they're grouted ducts, and again if they're steel, then you have to deduct half of each duct width from the total web width when you're calculating your shear resistance. If you've got plastic ducts or ungrouted ducts, it's a lot more severe, and you have to deduct 1.2 times the duct diameter, which is all about this sort of figure here. And what it's saying is if you've got a plastic duct, it's actually not very rigid, and the compression struts in that truss model will actually just tend to miss it. We will see something soft and just go round the duct and not go through the duct, even if it's grouted, because the plastic is flexible. And that sort of expansion, transverse movement, generates transverse tensions, which tend to split the concrete, which actually reduces its strength more than just simply the whole diameter. Now this is a bit unfortunate because one thing we're trying to do in industry is move people across to using plastic ducts because they're better for durability than steel ducts, and this punishes you for doing that. And so one of the committees that I'm involved with, we're trying to actually do a bit more testing on this to see if there's some justification to go back to using the same rules for steel and for concrete. Some of the tests show it makes no difference, and some of them show that plastic is quite a lot worse, so it just depends on which set of tests you take at the moment. If you've got, I haven't specifically got a slide there, but if you then need shear reinforcement, then the method of calculation is exactly the same as it is for reinforced concrete. So we only consider the design for the links. So we have the variable angle truss model, and we need Z, the lever arm, in that formula, and Z has to be based on the flexural analysis for the pre-stressing. We don't do a lot of segmental construction, I guess, generally across the group, and or at least not so much in Europe, but it's very common in other parts of Atkins, in Hong Kong and the Middle East, where actually a lot of what we do is segmental. And there is a new codified rule for segmental decks, which we haven't, I think generally haven't really been checking, but it is a real phenomenon. There have been failures as a result of not checking this. If you've got unbonded pre-stress, which you often have with segmental decks, then it's possible that because the steel is not actually bonded to the concrete, particularly the joints, you can actually get some pretty wide cracks or joint openings at the ultimate limit state, because there's nothing to actually physically bond it all together at the joint. And what that means is you end up with a restricted area for shear, because clearly the shear force, the shear strut can't pass through an open joint. And so what the code tells you to do is explicitly calculate for this situation from your ultimate limit state stress block how far the section decompresses and where the joint goes down to. And then you have to look at your strut model, again choosing your angle theta, and you have to position your links basically in a location close to the joint such that they will actually be picked up by that strut. And there's a limit to just how bad you can have your section, so you can't. The requirements of the ultimate limit state are such that you mustn't have the joint opening more than half the depth of the section, otherwise you're just going to end up with nothing left for shear. And so there have been some failures, and they manifest themselves in literally out the joint, the whole of the bottom of the section being swept out, because there's nothing to sort of anchor it back in if you distribute your links too far. That's flexural shear. Punching shear, we'll just go through this pretty quickly. In principle, things are much the same as we were before, but there are cosmetic differences. So we previously had perimeters at 1.5D, now they're at 2D. We previously had sort of square edges to all the perimeters, and now they're curved. But aside from that, there isn't much difference, and they've been moved out this way to allow us to use the same shear resistances for punching as for flexural shear. If you've got loads near the edge of the section, then again, the same as in BS 500, we have to consider sort of reduced perimeters, clearly, if we can actually sweep out to a free edge. And it's quite specific in what you do in situations like bases with variable depth. So I have seen arguments about this before. If you've got a perimeter, you know, and the section is tapering away, and you're supposed to be checking your perimeter at 2D, which depth do you use, the peak depth or the smaller depth? Well, the Eurocode is very clear, it's the bigger depth, not the smaller one on the perimeter. And that's simply because if you look at the failure line, it has to sweep right through that full depth of section, and the depth at the end of the perimeter is not relevant. Similarly, if you've got stepped cross sections like this, then you may have to check two perimeters. So you check one at the 2D perimeter in the thicker section, but then we also check effectively punching coming from the deeper section into the thinner section again. So we check another 2D perimeter out from the thicker depth of the section. The design punching stress we've got is basically what we're used to. It's the applied shear force divided by the perimeter area. But there is an additional term, beta, which we haven't previously had, although our buildings colleagues have had something similar. Just before I mention that, you'll see in calculating this that D is an average effective depth. So we don't kind of do the same approach we had in BS 500 where we work out the punching resistance by looking at the summation of the two sides, the two directions. We treat it as a whole using an average effective depth, which is basically just the average of the effective depth in the two directions. And there's a similar term for looking at the steel provision in the two directions as well for averaging that. The beta term is to do with any bending moment that's being transmitted at the same time as the punching force. So the easiest one to imagine is a pile cap with the piles coming up trying to punch through the base. And if we shove the pile cap for whatever reason, an impact or something, then we'll generate bending moments at the pile head connection. Now they have to be taken into account, and the reason for that is if we have bending at the same time as punching, then most of the punching force is going to be taken on the side where the bending moment is putting compression. So there's an extra term here, beta, which basically looks at the bending moment that you've actually got, and it turns that into a plastic bending distribution of shear force around the perimeter that you're checking. And that up and down force from bending adds on directly to the shear force that you get from the vertical load. And so it's all done with a plastic stress block. We haven't done that before. In terms of the design of piles, we've been unsafe not considering this before. But the reality is of having a sort of gamma C of 1.5 and various other gamma factors there, we've got away with it, but we haven't actually been achieving the sort of target reliability that the rest of the code achieves in punching design, things like that situation.
If you've got, say, checking punching across a corner or something with a car cap, taking that as an example, would you just take the average, because you'd have your bending moment across that, through that section, would you take the average bending moment, the average plastic stress?
I'll come on to that one in a minute because I've got a diagram that will hopefully help to explain it. So if we calculate our shear stress that's got the bending in there, then we then just compare it against the shear resistance for concrete on its own if we haven't got any links there. And that expression is the same as it was for flexural shear. If we've got a shear which exceeds the design shear resistance, then we have to basically put shear links in, obviously, and we then have to check a number of zones. So we have to check right against the loaded area, against the crushing stress, equivalent of VRD max. We have to check the zone where we're placing the shear reinforcement, and then we also have to establish the zone where we no longer need any reinforcement. And the reason for doing that is that there are then detailing rules about how far inside that perimeter we must stop the shear reinforcement. So when we're doing the basic shear design in the area where we're putting shear reinforcement in, we have an expression here for the shear resistance, and this one is different from the flexural shear requirement in that we do actually go back to the old BS 500 practice of adding a concrete term on top of a shear link term. But you'll see they're not fully additive. The concrete term, we only take 75% of it, and the shear link term, even though we're considering a 2D perimeter, so we should really have 2D's worth of links, we only take 1.5 times the 2D length. And that's the same justification, or the same reason as I mentioned earlier about the shear enhancement close to supports, is that test results show that the links, if you put them very close to the loaded area and close to the perimeter, they don't yield, they don't actually participate. So it's only the 1.5D in the middle of the 2D that actually does anything in the resistance. One of the problems with using that formula is that you need to have ASW over SR. So this is the amount of link, basically the links per millimeter, if you like. And it's all right if you have links provided in the way that they're shown in the code, like radially or like a cruciform, because you have the same number of links on each successive perimeter per millimeter. But the reality is nobody puts links in like that normally, like a sort of fanning out. And generally we don't put links in like that. We put them in as a grid all the way around, an orthogonal grid. So you either conservatively miss out all those portions if you're using the Eurocode formula, or an alternative version, which is in the notes and the Thomas Telford guide, is to look at the 2D perimeter that you're considering. For compatibility with the formula, just look at the links which are in the inner 1.5D of the 2D. Basically just sum up, or basically provide in that area there enough links to carry the shear force, the shear stress minus the concrete contribution. So that basically allows you to just consider all of the links in that shaded zone, rather than just a formula based on links per spacing, which actually would then miss out some of the links that you're providing. This basically then just shows you how you detail up the links. So what we do need to do is establish the perimeter where links are no longer required. So that basically just means calculating a value of U outer such that we satisfy this equation here, where the shear force is carried entirely by the concrete term, the VRDC term. We don't need any links. So that gives us a perimeter as shown here, perimeter A, where we don't need links anymore, and then we have to basically stop or start our link provision 1.5D in from that outer edge. And that just makes sure that we don't get a link, we don't get a failure with inside that plane, that way it doesn't pass through a leg of a link. For bases, and with the example we've got in the handout is a base. These are sort of pad foundations. Then the Eurocode specifically talks about making sure we consider the relief of soil pressure. So we have to check typically a perimeter on the outside of the column on the base, one at a D away and one at 2D away. The perimeter around the column clearly has very little upward soil pressure resisting the downward load because it's close to the pier. But out on this column out here, in one direction we've got the load from the column, but in the other direction, reducing the shear stress is a huge amount of soil pressure pushing up. So the way this situation is addressed, it defines the shear force as BD red for reduced, meaning the actual net shear force on the perimeter from the column load minus the shoal pressure in the other direction. And then we use that reduced pressure and any bending moment that's present at the same time to calculate what our actual shear stress on the perimeter is. And then we then compare that against the shear resistance without concrete. And again, unfortunately the code is full of slight sort of disconnects. In this particular scenario, because it's telling you to check perimeters inside 2D, if you don't include shear enhancement on the perimeters inside 2D, you just get a nonsense because it just gets progressively more critical as you come inside. So when you're checking punching and you're allowing for reverse soil pressure coming up, the formula is again modified to include 2D over AV in the shear resistance term. It's a bit of a shame it's not consistent throughout the different parts of the Eurocode, but I think in 5 years' time when it's updated, because nobody likes this idea of reducing loads, unenhancing loads, I think it will actually all become properly compatible, but at the moment it isn't, I'm afraid. But basically we also need to check flexural shear across the base. Again, that's just the same as we've done now. And the example covers that. When we get onto piles, then we have the scenario here of how many planes do we have to check. If we've got a pile base, then we have to check a flexural shear plane across the base in the same way as we would have done previously. But what do we do about punching? Because more often than not, the pile spacings are such that they all interfere with each other. If you draw a 2D perimeter around the pile and an adjacent pile, they'll all start intersecting. And the pile sort of nearest the column, like in this case here, we've got a sort of rectangular column. The 2D perimeter from this outer pile nicks through the base. And the Eurocode doesn't actually tell you what to do in this situation. So we've had to make up some suggestions in the books, basically. And there are, I haven't mentioned them so far today, but there are some BSI documents that have been produced as well, some PDs, published documents, and they're generally either called recommendations for or background to the UK National Annex. These documents have no status, really, in themselves. They're just guidance material. The Highways Agency are looking to make some parts of them mandatory, which is why we haven't got BD 100 at the moment, because I don't think, well, Europe basically scrutinising, and I don't think when they actually start looking at these proposals to try and make other documents mandatory that they're going to like it. So the BSI PD that goes with recommendations for using Eurocode 2 Part 2 basically lifts out the requirement, well, the recommendations from that book on the concrete. And it says when you're checking an outer pile like this, just check the resistance on the 2D perimeter, ignoring the fact that it's passing through the support. So don't try and reduce it such that it misses the support and include enhancement. Just consider the full 2D perimeter and just ignore the presence of the support. The book suggests that we also do a plane across nicking the pile cap, which was the old approach we used in BS 500, which was following Les Clark's requirements. So the Thomas Telford guide recommends still doing that. In the end, the BSI committee that I worked on that put the PD together for Eurocode 1992 decided that was unnecessary. So the PD only recommends checking the 2D curve perimeter, perimeter A, and not bothering to check perimeter C. There's been some more testing done at Southampton University recently that supposedly justifies that. Coming back to the question of what you do if you've got combined moment at the time, you'd therefore be having to look at the moment transmitted, and it would be taken purely as a shear on the curved plane, on plane A. I don't think there's a formula given to you in the code for doing that, unfortunately. So you'd have to kind of look at the lever arm between the pile and the perimeter and work out a set up and down forces to use on that curved perimeter. Just very quickly, I'm not going to go through longitudinal shear in any detail, I'll just bring it to your attention. If you've got flanged members, like really this is box girders, then we have to check shear in the flanges. And it comes from a sort of strut and tie type approach. The middle of the three diagrams is an elevation on the web. The top part's the top flange and the bottom part's the bottom flange, and it is just showing that the vertical compression struts in the web hit the top flange and then spread out into the web, and the spreading out of the compression into the web generates a transverse tension. And that's basically what you're trying to design for with your longitudinal shear. You're trying to hold the flange onto the web to allow for that spreading. And there's a simple formula in the code for doing that. You basically calculate your shear stress based on the vertical stress times the reduction factor for the width of web, the width of flange to the side of the web that you're considering as a fraction of the total flange. So if you like, you're taking the total flange force and then just working out what part of that flange force is in the flange that you're trying to tack on. So you're reducing the shear for that. And then there's another factor beta, which takes account of the fact that actually some of the force that you've got is actually in the web as well, and it actually doesn't need to be attached to the web because the force is already in the web. And again, I won't go through this now, but there's a truss model behind the formula for longitudinal shear resistance, and it's really the same background to the one for the vertical shear resistance, but there are different limitations on the angles. You can't go to quite such a flat truss angle in the design of a flange as you can for the design of a web. There are some rules if you're designing for longitudinal shear between webs and flanges. The reinforcement that you're using, the transverse reinforcement that you're going to use for longitudinal shear, may also be doing a job for transverse bending in the flange. And again, the code gives you some rules for how you add those two reinforcements together. You don't need to add the full combination of the two. There's a slightly curious rule which actually works if you look in more detail, but it looks a bit odd if you just read it, which basically says that when you're designing the transverse reinforcement, you provide the greater of that you need for longitudinal shear on its own, or half what you need for longitudinal shear plus all of what you need for bending. So you just basically look at those two extremes and provide the greater of the two. We haven't got time to go into why it works, but it does work. And then if you've got concretes cast at different times, so this might be your typical sort of deck slab sitting on top of a pre-tension beam, then again we have to check interface shear. So we need to calculate our shear flow. And the important thing here is that the shear flow is calculated in the same way as we were just kind of looking at for a flange. So we don't use the elastic shear flow anymore. We used to use VAY over I. We don't use that anymore. We use the actual shear flow that suits the actual stress block that we've used in calculation. So if we've used this stress block, we need to use that to work out what the force is in the flange and in the web at different levels, and then we use that for the change of that force along the beam to work out the shear flow. But it's basically summed up in the expression here. We actually just take the average. It works out that we actually just take the average shear stress and multiply it by this ratio beta, where beta is the ratio of the force in the flange we're trying to attach divided by the total force in the compression zone. It's actually quite simple to do, but that effectively gives you the plastic shear flow instead of the elastic shear flow.